So this is by the time you're done with this, you ought to be able to calculate an EMF induced on a conductor. So first off, what I want you to do is look at this picture here. Okay, we decided that, gentlemen, we decided that in this picture, okay, that the current is going to flow, and let's figure this out, right? What's happening? Are we increasing or decreasing flux? And the idea is that this thing here is sliding relative to this U-shaped bar, right? And so as it slides, this area is getting bigger and bigger, yes? Okay, so are we gaining or losing flux? Gaining which way? Into the page. And so if we gain into the page, we oppose that by making out of the page, right? So in this picture here, this stuff's going to go anti-clockwise, right? So that was one way that we did it, okay? Now, the next thing that I want you to do here is I want you to think about what happens to this wire even if that other bar is not there. If that bar is there, a current flows, okay? But if that bar is not there, you still get an EMF, and that's because charge is going to get moved on that bar, okay? Here's why. Well, if you're a positive charge and you're moving on that bar, you're moving that way, right? The magnetic field is into the page, and you're going to get forced up the bar. Now, of course, positive charges don't move. Really, it's the negative charges that go down, but it doesn't matter. It's the same thing, right? So there will exist an EMF on that bar due to the fact that you're moving it through that field, which is kind of cool, right? And the top is going to be the positive side. The bottom will be the negative side, okay? And then the formula for this we can get, because it's the EMF is NBA, right? So it's BA over T, basically, right? And you know, I'm not going to do something with an angle. I guess we've got the cosine, right? Okay. But I'm just going to take that off to derive the formula. Okay. And then if you look at this thing, we've got this thing there. This is L. This thing here is moving with some velocity v, right? Which really is x divided by t, isn't it? Right? Okay. And then this area that it moves through, because in a little bit of time it's going to be here having moved distance x. Isn't that right? Okay, so this area in here is L by x, right? So this becomes B x times L over T, right? Okay, and nobody wants to say Bixel over T, do they? That's no fun, right? Okay, well, what is x over T? That's our velocity, right? And so EMF is equal to BV L, right? And then if there's some angle, right, that's going on, then we've got to put the cos theta in there, okay? But in the data packet, they just give you BVL, so apparently they're only going to give you problems where it's at a right angle to it, right? But were it not at a right angle, why we would, yeah. We'd have to do some cosine or something clever like that. And then we've already shown the direction of the EMF with the cross product, right? The direction of the EMF is that the positive charge moves to the top, so therefore the top side of this one is going to be the positive side, right? You just do the vector cross product like this, right? You pretend you're a positive charge on the wire, right? So the velocity is that way, magnetic field's into the page, positive charge is going to move up the wire. So in this case, the top is positive, bottom is negative, just by subtraction. Oh, because yeah, we're going to want to know which side's the positive side. Yeah. And then I think you guys should try some of these, yeah? Should we? Oh, I think we should. Okay, so the wire moves to the right at 12.5 meters per second. what is the EMF generated? So you must have you got the magnetic field, you've got the length of the wire. It's in centimeters. That's a little bit tricky, you know. $11 in the bottom is, yeah, that's right. Mm-hmm. Mm-hmm. Yeah, that's right. You got it. What does it say on the bottom? Is that bottom? I like that. You got it. Yeah. Yeah, your sig figs are a little enthusiastic there. We only have 2 sig figs.
I put your actual sig fig number down here because I knew you'd say that.
Yeah, yeah, yeah. So this is 1.7 Teslas times 12.5. Huh?
The ink is dried onto the black one. Rag and
There's methanol, that'll take it off.
I don't remember if it was ethanol or methanol. And again, it doesn't matter which it is.
Takes it 1.7. And then are we good? The velocity is that way, magnetic field is that way, and the positive moves to the bottom. Yeah? Should we try another nutter butter?
Yep.
Like, oh, look at that. How long does the wire need to be to generate a oh my gosh, this time I'm not asking you for the EMF, I'm asking you for help. 45 volts, and what end is positive?
Wow, that is fast.
Yeah.
Oh, that's pretty fast.
They did this, I think they did an experiment with this with the Earth's magnetic field, which is pretty weak, but they did it with a tether on like a space shuttle, right? So the space shuttle is going like 17,000 miles per hour, right? And I think it, like, the tether just like blew apart or something like that. Yeah.
Is that the right?
That's a little enthusiastic for the length. So your velocity's that way. Magnetic field's into the page. The bottom. Yeah, there you go. Yeah. The bottom side's going to be the positive side, right? Yeah. Yeah, you got it. Yeah. Yep. Yeah. What units? I mean, give me sig figs.
Here's your alcohol back.
My alcohol. Thank you for my alcohol. I'm dispensing alcohol to minors. Not for the purposes of consuming, however.
Of course, of course.
Yes, yes. Bottom is positive, yeah. Yep.
That's part of the answer.
Yeah. Yeah. Bottom.